Hello everyone, and welcome to my channel. This is an educational channel, and we take deep dives into some great theories of everything, and show you how they work, um, and hopefully help you to adapt them to your own situation, your own paradigm shifting, and your awakening to 5D consciousness, forming your holistic worldview, and anything else that you might be able to glean from these great theories of everything. Today is our 489th video on the reciprocal system of theory from Dewey B. Larson. And Mr. Larson's theory is not really out there. I seem to be like the only person on the internet that's doing reciprocal system videos in bulk. You can find a few here and there, but I don't think anybody's done almost 500 videos on the reciprocal system. And it's a darn shame, because Mr. Larson put together a generalized theory of everything and made great strides in the course of 60 years up until his death in 1990 in showing how it works, and has at least a small group of people that are still trying to kind of put it together. Now, Larson did make a few mistakes, in my opinion, and that's kind of set the progress back. But, you know, the truth always comes to the surface eventually. And so you be best to pay attention to these videos, because sometime in the near future, everyone is going to need to learn this, because it is going to be the basis of all our sciences in the future. Not only our sciences, but all our entire educational curriculum and religious curriculum and everything else. You're going to need to learn the reciprocal system. And so I am not, you know, maybe a perfect messenger for this, because I don't understand the reciprocal system in all its ins and outs at this point. But I think I understand it well enough to at least present it to you, especially if you are some kind of, you know, a digger, and that you can, you know, do some research on your own, and, you know, maybe fill in some of the blanks that I leave. But mainly what I do on this channel is go through Larson's own words. So we mostly read his writings and some of his other followers as well. You know, because I don't feel like I can, you know, summarize what he says as well as his own words. So today we're looking at his 1987 book, Basic Properties of Matter. We're in chapter 13 of that book on electrical charges. And this book is primarily on chemistry. It's one of the books that he wrote where he basically, you know, Larson in 1959, he arrived at his two fundamental postulates that he put out, and basically two sentences about how he believed the universe operated. And then he elaborated those postulates into a theoretical universe. And then in books like this one here, he compares his theoretical universe, what the universe would look like if his postulates were correct, with the empirical universe of the legacy scientists. So the measured, laboratory measured and compiled scientific tables and so on for the basic properties of matter, in this case, like the melting point and the specific heat and the compressibility. And in this case, this chapter is on electric charges. Now, if you want a more detailed summary of Larson's reciprocal system, otherwise known as a universe of motion. You can watch any of my first 474 videos on this subject, where I go into it a little bit in a little bit of detail. But I'd like to try to get through the text here today. So we're going to start up right away. I pretty much am going to assume that you know enough to follow along here. But if you don't, check out one of my first 474 videos on this topic. Okay. The so-called fundamental forces of nature, the presumably autonomous forces that are currently being called upon to explain the origin of the basic physical phenomena, are necessarily properties of underlying motions. They cannot exist as independent entities. Every fundamental force must originate from a fundamental motion. This is a logical requirement of the definition of force, and it is true regardless of the physical theory in whose context the situation is viewed. Present-day physical science is unable to identify the motions that the definition of force requires. An electric charge, for instance, produces an electric force, but so far as can be determined from observation, it does this on its own initiative. There is no indication of any antecedent motion. This apparent contradiction of the definition of force is currently being handled by ignoring the requirements of the definition and treating the electric force as an entity generated in some unspecified way by the charge. The need for an evasion of this kind is now eliminated by the identification of the charge as a rotational vibration. It is now clear that the reason for the lack of any evidence of a motion being involved in the origin of the electric force is that the charge itself is the motion. The electric charge is thus a one-dimensional analog of the three-dimensional motion of an atom or particle that we identified as mass. The space-time dimensions of mass are time to the third over space to the third. In one dimension, this is time over space. Rotational vibration is a motion similar to the rotation that constitutes mass, differing only in the periodic reversal of scalar direction. It follows that the electric charge, a one-dimensional rotational vibration, also has the dimensions T over S. The dimensions of the other electrostatic quantities can be derived from those of charge. The electric field intensity, a quantity that plays an important part in many of the relations involving electric charges, is the charge per unit area. T over S times 1 over S to the second power equals T over S to the third. Electric field intensity. The product of field intensity and distance, T over S to the third times S equals T over S squared is a force, the electric potential. For the same reasons that apply to the production of a gravitational field by a mass, the electric charge is surrounded by a force field. However, there is no interaction between mass and charge. As brought out in Chapter 12, a scalar motion that alters the separation between A and B can be represented in the reference system either as a motion AB, a motion of A toward B, or a motion BA, a motion of B toward A. Thus, the motions A, B, and BA are not two separate motions. They are merely two different ways of representing the same motion in the reference system. This means that scalar motion is a mutual process and cannot take place unless the objects A and B are capable of the same kind of motion. Consequently, charges, one-dimensional motions, interact only with charges, masses, three-dimensional motions, only with masses. The linear motion of the electric charge, analogous to gravitation, is subject to the same considerations as the gravitational motion. As noted earlier, however, it is directed outward rather than inward, and therefore cannot be added directly to the basic vibrational motion in the manner of the rotational motion combinations. This restriction on outward motion is due to the fact that the outward progression of the natural reference system, which is always present, extends to the full unit of outward speed, the limiting value. Further outward motion can be added only after an inward component has been introduced into the motion combination. A charge can therefore exist only as an addition to an atom or subatomic particle. Although the scalar direction of the rotational vibration that constitutes the charge is always outward, both positive time displacement and negative space displacement are possible, as the rotational speed may be either above or below unity, and the rotational vibration must oppose the rotation. This introduces a rather awkward question of terminology. From a logical standpoint, a rotational vibration with a space displacement should be called a negative charge, since it opposes a positive rotation, while a rotational vibration with a time displacement should be called a positive charge. On this basis, the term positive would always refer to a time displacement, low speed, and the term negative would always refer to a space displacement, high speed. Use of the terms in this manner would have some advantages, but so far as the present work is concerned, it does not seem advisable to run the risk of adding further confusion to explanations that are already somewhat handicapped by the unavoidable use of unfamiliar terminology to express relationships not previously recognized. For present purposes, therefore, current usage will be followed, and the charges on positive elements will be designated as positive. This means that the significance of the terms positive and negative with respect to rotation is reversed in application to charge. In ordinary practice, this should not introduce any major difficulties. In this present discussion, however, a definite identification of the properties of different motions entering into the combinations that are being examined is essential for clarity. To avoid the possibility of confusion, the terms positive and negative will be accompanied by asterisks when used in the reverse manner. On this basis, an electropositive element, which has low-speed rotation in all scalar dimensions, takes a positive asterisk charge, a high-speed rotational vibration. An electronegative element, which has both high-speed and low-speed rotational components, can take either type of charge. Normally, however, the negative asterisk charge is restricted to the most negative elements of this class, those of division 4. Many of the problems that arise when scalar motion is viewed in the context of a fixed spatial reference system result from the fact that the reference system has a property, location, that the scalar motion does not have. Other problems originate for the inverse reason. Scalar motion has a property that the reference system does not have. This is the property that we have called scalar direction, inward or outward. We can resolve this latter problem by introducing the concept of positive and negative reference points. As we saw earlier, assignment of a reference point is essential for the representation of a scalar motion in the reference system. This reference point then constitutes the 0 point for measurement of the motion. It will be either a positive or a negative reference point, depending on the nature of the motion. The photon originates at a negative reference point and moves outward toward more positive values. The gravitational motion originates at a positive reference point and proceeds inward toward more negative values. If both of these motions originate at the same location in the reference system, the representation of both motions takes the same form in that system. For example, if an object is falling toward the Earth, the initial location of that object is a positive reference point for purposes of the gravitational motion, and the scalar direction of the movement of the object is inward. On the other hand, the reference point for the motion of a photon that is emitted from that object and moves along exactly the same path in the reference system is negative, and the scalar direction of the movement is outward. One of the deficiencies of the reference system is that it is unable to distinguish between these two situations. What we are doing in using positive and negative reference points is compensating for this deficiency by the use of an auxiliary device. This is not a novel expedient, it is common practice. Rotational motion, for instance, is represented in the spatial reference system with the aid of an auxiliary quantity, the number of revolutions. Ordinary vibrational motion can be accurately defined only by a similar expedient. Scalar motion is not unique in its need for such auxiliary quantities or directions. In this respect, it differs from vectorial motion only that it has a broader scope and therefore transcends the limits of the reference system in more ways. Although the scalar direction of the rotational vibration that constitutes the electric charge is always outward, positive asterisk and negative asterisk charges have different reference points. The motion of a positive asterisk charge is outward from a positive reference point toward more negative values, while that of a negative asterisk charge is outward from a negative reference point toward more positive values. Thus, as indicated in the accompanying diagram, figure 20, while two positive asterisk charges, line A, move outward from the same reference point and therefore away from each other, and two negative asterisk charges in line C do likewise, a positive asterisk charge moving outward from a positive reference point, as in line B, is moving toward a negative asterisk charge that is moving outward from a negative reference point. It follows that like charges repel each other while unlike charges attract. As the diagram indicates, the extent of the inward motion of unlike charges is limited by the fact that it eventually leads to contact. The outward movement of like charges can continue indefinitely, but it is subject to the inverse square law and is therefore reduced to negligible levels within a relatively short distance. Electric charges do not participate in the basic motions of atoms or particles, but they are easily produced in almost any kind of matter and can be detached from that matter with equal ease. In a low-temperature environment such as that on the surface of the Earth, the electric charge plays the part of a temporary appendage to the relatively permanent rotating systems of motions. This does not mean that the role of the charges is unimportant. Actually, the charges often have a greater influence on the outcome of physical events than the basic motions of the atoms of matter that are involved in the action. But from a structural standpoint, it should be recognized that the charges come and go in much the same manner as the translational, kinetic, or thermal motions of the atom. Indeed, as we will see shortly, charges and thermal motion are, to a considerable degree, interconvertible. The simplest type of charged particle is produced by imparting 1 unit of one-dimensional rotational vibration to the electron or positron, which have only one unbalanced unit of one-dimensional rotational displacement. Since the effective rotation of the electron is negative, it takes a negative asterisk charge. As indicated in the description of the subatomic particles in Volume 1, Each uncharged electron has two vacant dimensions, that is, scalar dimensions in which there is no effective rotation. We also saw earlier that the basic units of matter, atoms and particles, are able to orient themselves in accordance with their environments. That is, they assume the orientations that are compatible with the effective forces in those environments. When produced in free space, as, for instance, from the cosmic rays, the electron avoids the restrictions imposed by its spatial displacement, such as the inability to move through space, by orienting in such a way that one of its vacant dimensions coincides with the dimensions of the reference system. It can then occupy a fixed position in the natural system of reference indefinitely. In the context of a stationary spatial reference system, this uncharged electron, like the photon, is carried outward at the speed of light by the progression of the natural reference system. In this electron, if this electron enters a new environment and becomes subject to a new set of forces, it can reorient itself to conform to the new situation. On entry into a conducting material, for instance, it encounters an environment in which it is able to move freely, inasmuch as the speed displacement in the motion combinations that constitute matter is predominantly in time, and the relation of space displacement of the electron to the atom time displacement is motion. Furthermore, the environmental factors favor such a reorientation. That is, they favor an increase in speed above the previous unit level in a high-speed environment and a decrease in a low-speed environment. The electron therefore reorients with its active displacement in the dimensions of the reference system. This is either a spatial or a temporal reference system, depending on whether the speed is below or above unity. But the two systems are effectively parallel. They are actually two sections of a single system, as they represent the same one-dimensional motion in two different speed ranges. Where the speed is above unity, the representation of the variable magnitude is in the temporal coordinate system, and the fixed position in the natural reference system appears in the spatial coordinate system as a movement of the electrons, the electric current, at the speed of light. Where the speed is below unity, these representations are reversed. It does not follow that the progression of the electrons along with the conductor takes place at these speeds. In this respect, the electron aggregate is similar to a gas. The individual electrons are moving at high speeds, but in random directions. Only the net excess of the motion in the direction of the current flow, the electron drift as it is usually called, is effective as a unidirectional movement. This idea of an electron gas is generally accepted in present-day physics, but it is conceded that the simple theory runs into greater difficulties when examined in more detail. As noted previously, the prevailing assumption that the electrons of this electron gas are derived from the structures of the atoms encounters many problems. There is also a direct contradiction in the specific heat values. The electron gas would be expected to contribute an extra 3/2 R to the specific heat of metals, but no such specific heat increment is found experimentally. The theory of the universe of motion supplies the answers to both of these problems. The electrons whose movement constitutes the electric current are not derived from the atoms and are not subject to the restrictions that apply to this region, to this origin. The answer to the specific heat problem is provided by the nature of the electron motion. The motion of these uncharged electrons, units of space, through the matter of the conductor is equivalent to motion of the matter through extension space. At a given temperature, the atoms of matter have a certain speed relative to space. It is immaterial whether this is extension space or electron space. The motion through electron space, movement of the electrons, is part of the thermal motion, and the specific heat due to this motion is part of the specific heat of the atom, not something separate. Once the reorientation of the electrons takes place in response to the environmental factors, it cannot be reversed against the forces associated with those factors. The electrons therefore cannot leave the conductor in the uncharged state. The only active property of an uncharged electron is a space displacement, and the rotation and the relation of this space to extension space is not motion. However, an electron can escape from the conductor by acquiring a charge. A combination of rotational motions with a net displacement in space can move only in time, as indicated earlier, and one with a net displacement in time can move only in space, as motion is a relation between space and time. But unit speed is unity in both time and space. It follows that a motion combination with a net speed displacement of 0 can move in either time or space. Acquisition of a unit negative asterisk charge, usually actually positive in character, by the electron, which in its uncharged state has a unit negative displacement, reduces the net speed displacement to 0 and allows the electron to move freely in either space or time. The production of a charged electron in a conductor requires only the transfer of sufficient energy to an uncharged electron to bring the existing kinetic energy of that particle up to the equivalent of a unit charge. If the electron is to be projected into space, the additional amount of energy is required, to break away from the solid or liquid surface and to overcome the pressure exerted by the surrounding gas. At energies below this level, the charged electrons are confined to the conductor in the same manner as when they are uncharged. The necessary energy for the production of the charge and the escape from the conductor can be supplied in a number of ways, each of which therefore constitutes a method of producing freely moving charged electrons. A convenient and widely used method furnishes the required energy by means of a voltage differential. This increases the translational energy of the electrons until they meet the requirements. In many applications, the necessary increment of energy is minimized by projecting the newly charged electrons into a vacuum rather than requiring them to overcome a gas pressure. The cathode rays used in X-ray production are streams of charged electrons projected into a vacuum. The use of a vacuum is also a feature of the thermionic production of charged electrons, in which the necessary energy is imparted to the uncharged electrons by means of heat. In photoelectric production, the energy is absorbed from radiation. Evidence of the electron as a free charged unit is usually of brief duration. Within a short time after it has been produced by one transfer of energy and ejected into space, it again encounters matter and enters into another energy transfer by means of which the charge is converted back into thermal energy or radiation, and the electron reverts to the uncharged condition. In the immediate neighborhood of an agency that is producing charged electrons, both the creation of charges and the reverse process that transforms them back into other types of energy are going on simultaneously. One of the principal reasons for the use of a vacuum in electron production is to minimize the loss of charges by way of this reverse process. Charged electrons in space can be observed, that is, detected by various means, and because of the presence of charges, they are subject to electric forces. This enables control of their motions, and unlike its elusive uncharged counterpart, the charged electron is an observable entity that can be manipulated to produce physical effects of various kinds. It is not feasible to isolate and examine individual charged electrons in matter as we do in space, but we can recognize the presence of such particles by evidence of freely moving charges within the material aggregates. Aside from the special characteristics of charges, these charged electrons in matter have the same properties as the uncharged electrons. They travel readily through good conductors, less readily through poor conductors. They move in response to voltage differences. They are restrained by insulators, which are substances that do not have the necessary open dimensions to allow free electron motion, and so on. In their activities in and around aggregates of matter, these charged electrons are known as static electricity. Okay, that is the end of the chapter. Chapter 13 on electric charges. Chapter 14 is called The Basic Forces, and we will start that chapter tomorrow. Larson's theory on electricity, especially electric charges, is subject to some dispute by some of his followers. Dr. Bruce Perrett has kind of overhauled a lot of Larson's stuff as far as electricity is concerned, and we will go through Dr. Perrett's, along KVK Nehru's, different versions of this as well. And I have to admit, I do not understand Larson's electronic theory as well as I understand the rest of his stuff. So I'm pretty lost about this stuff as well. But be that as it may, we will proceed on. And thanks for tuning in, and have a great